Okay, so we got another video. We got a video that's completely different than what we've been talking about so far. We've spent a lot of time solving equations and getting really good at graphing, and that's great because we use all that stuff moving forward. In fact, a lot of people never practice it. They get to stuff like calculus 3 and forget how to graph lines. So hopefully that's not going to be you. But now another thing that's going to get us ready for some higher levels of mathematics is talking about exponents and the rules that we use to simplify exponents, to work with exponents. What this does, it allows us to factor and to distribute and to deal with some fractions in some ways that aren't obvious. Those have to deal with exponent rules. And we're going to start that in this video when I introduce what exponents even are. So we'll talk about exponents, how to use them. I'm going to treat them, kind of go from scratch here and deal with exponent rules in the next few videos. So the first thing is really understanding what exponents mean. So we've seen exponents probably up at this point, and we know that somewhere in the order of operations, they're here, and I'll reference order of operations a lot when we talk about this. We know that we do parentheses first, and then come this thing called exponents. And then multiplication and division are on the same level. One's not really higher. They're done from left to right. And then after that, we have addition, subtraction. So there are 4 levels of operations. There are parentheses, and then exponents, and then multiplication and division is 1 level. And they're accomplished as moving left to right across an expression. And then we have addition, subtraction as the last level. I'm going to say something right now that is going to cover you for exponents for the rest of your life. What you do with exponents is one operational level below what you see. I want that to stick in your head as we go through a lot of these next videos, but I'm introducing it right now because what you do with exponents, the operation that you actually do, is one level below the operation that's written on your paper. One level below what you see. What's one level below me? If you see exponents raised to exponents, you will be multiplying. If you see multiplication, you will be adding. If you see division, you will be subtracting. If you see addition involving exponents, you will be doing nothing with those exponents. You keep them the same. If you see subtraction with some exponents, you'll be doing nothing with those exponents. You'll keep them the same. That will cover you pretty much through all the exponent rules. I'll show you exactly how to deal with it. I'll show you where you can distribute, where you can't. But it all comes down to, what are exponents? What do they even mean? Well, as we start building operations, we start repeating previous operations. For instance, what multiplication really is repeated addition of the same number. So 5 times 3, you literally could do 3 plus 3 plus 3 plus 3 plus 3 5 times. That's where multiplication stems from. It's repeated addition of the same number. Well, exponents are repeated multiplication of the same number. That's what these really are. So when we talk about exponents, exponents are repeated multiplication. And we can show that. So imagine that you saw the same number multiplied over and over and over and over and over again. Eventually it gets really tiresome to write that out. I mean, if we had b times b times b times b, a whole bunch of times, let's say n times. Well, we could write out b times b times b times b times b times b. That's not wrong, but there's a much more concise way to write it. Just like multiplication, we could write out 3 plus 3 plus 3 plus 3 plus 3. But what if you had to do that 100 times? Do you really want to write out 3 plus 3 plus 3 plus 3 100 times? Or would you rather write 3 times 100? Well, you see, these operations save us time and space and energy. So when we need to repeatedly multiply the same number over and over again, exponents accomplish that and allow us to write it quickly and allow us to do the operation quicker when we see some of the patterns. So instead of writing out b times b times b times b times b n times, we can keep that number that's being repeatedly multiplied, we treat that as our base. So we'll say our base is b. How many times we're actually repeating that multiplication, that is called an exponent or a power. N. So if we want to represent that a number b is being multiplied over and over and over again this many times, n times, we can write that as b to the n. Let me give you a few examples. One thing you might notice right off the bat is that in order to use an exponent to represent multiplication, you have to have the exact same number being multiplied. I can't do 7 times 7 times 5 times 2 and represent that as one exponent. So that b, it can't change. It's got to be repeated multiplication. So right now, our base, what we call the number that's being multiplied over and over again, that base is 7. So we can write this as an exponent, 7, to, well, the exponent would be a base of 7, an exponent of how many times have you multiplied the 7 times itself? Let's see, 1, 2, it'd be 4. That exponent is written above and to the right of our number. It's called a superscript. And how we say it is important. If we have an exponent of 2 or 3, we have some special words for that. We can say 7 squared or 7 cubed for the 2 and 3 respectively. But you can say any exponent as base to the exponent power. So in this case, 7 to the 4th power, 7 to the 2nd power, 7 to the 3rd power, 7 to the 5th power. That works all the time. So we don't want to say stuff like 7-4. That doesn't make sense. Or 10-4. No, that's what you say on the CB radio when you're talking to your trucker buddies. We don't say that. No, we say 7 to the 4th power because we want to be very clear on what we're talking about. We're talking about repeated multiplication, and that will be clear to everybody who hears that. Or 7 squared, 7 cubed, that's fine. But after we get higher than 3, there's no real special way to say those powers. Now, here's what it does mean. Here's what it doesn't mean. What it doesn't mean is 28. Yes, we're multiplying. But we're not multiplying the base times the exponent. We're not doing that. We're multiplying the base times itself 4 times, repeatedly multiplying a 7. 7 times 7 is 49, times another 7, like 343 or something. I don't remember what it is. But we multiply, what would that be? 7 times another 7? Whatever. Well, we're multiplying 7 times 7 times 7 times 7. That's a large number. It's not 28. It's way more than 28. We eclipsed 28 by just multiplying 7 times 7. I mean, that's already 49. So when we're doing exponents, please don't misconstrue the operation. Yes, we're multiplying. It's what it represents. But it doesn't represent multiplying the base times the exponent. It's the base times the base times the base times the base, whatever the exponent says. That's an important concept. Now, we can do a lot of other things. We can represent fractions if you want. One-third to the 5th power. Well, what that means is we're repeating that fraction over and over and over and over and over until we run out of that exponent. So 1/3, 1, 2... excuse me, 3, 4, 5 times. One thing that we're going to show right here is some of the rules. So if you've repeatedly multiplied the same fraction over and over again, well, we also know how to multiply fractions. We know that the numerator gets multiplied 1 times 1 times 1 times 1 times, well, that's 1 to the 5th. And the denominator gets multiplied 3 times 3 times 3. That's 3 to the 5th. Right here, this is one of the rules that we're going to unpack in a future video, is that if you have a fraction raised to an exponent, yeah, it means that fraction repeatedly multiplied, but inherently that multiplies the numerator times itself and the denominator times itself. So what this shows is that anytime you have a fraction and there's no addition subtraction in here, that exponent gets applied to both the numerator and the denominator. That's cool. That's one of the rules that we're going to be talking about in a minute. Another big misconception that people deal with is how to deal with negatives in exponents. I need to show you an example. It's a really important one. So I hope I have your complete attention here. A lot of people jack this thing up. So huge focus for like the next minute and a half. These are not the same number. They're not the same answer. They don't mean the same thing. A lot of people think they mean the same thing. They don't. They don't. What this means is the entire expression, -2, being raised to the 6th power. This is repeating this -2 6 times. That's what that means. 1, 2, 3, 4, 5, 6 negative 2's being repeatedly multiplied. That's exactly what this is talking about. Now, negative 2 to the 6 like this. This is not saying the same thing. You see, the way that exponents work, the way that ordered operations work, exponents happen before any multiplication, before any division, before any addition, subtraction. So any of those operations that you can pull out do not get the exponent applied. Now, here's why I'm saying this. If you can separate out a negative, which you can, this can be written as negative 1 times 2 to the 6th. The exponent applies to the 2. It doesn't even touch the negative. It doesn't even touch the negative. It doesn't apply to the negative 1. Exponents only apply to the immediate factor, thing being multiplied, the immediate factor that they're above. So that 6 would apply, the exponent of 6 would be applied to the 2, but not the negative. In this case, even if I try to pull out a negative, it's still in the parentheses. It's housed in there. It can't get away. We can't separate it from the exponent. That exponent says, I'm going to raise everything in here to the 6th power, including the negative. This says, I'm going to raise this immediate thing to the 6th power, but it does not include the negative. The way to remember this is in parentheses with the exponent. No parentheses, not with the exponent. So what this really is the opposite, or the negative, of 2 times 2 times 2 times 2. That's what that means. That's a big difference. So I need you to really get it. In parentheses, that negative goes with the number. In parentheses, with the number. No parentheses, it does not go with that number. Now, sometimes we're going to get the same answer. What times? If that's like a 5 or a 3 or a 1 or a 7 or an odd, then you'll have that extra negative. This is always going to be negative. Get that straight. This is kind of cool. If you don't have parentheses and you have a negative, your answer is going to be negative, 100%. Because it's going to say negative, and that negative never gets multiplied by another negative. This is a big deal. I need you to get it. In parentheses with the number, not in parentheses, your answer is going to be negative. You're going to have one negative times that number being repeatedly multiplied. It's a kind of an interesting deal there. Can you see how people would make mistakes? Like, it's very easy to make mistakes on this. One of these answers is going to be positive. Negative times a negative, positive, times another negative, negative, positive, negative, positive. This is certainly going to be negative. What would happen if I changed this to 7? Would we get a positive or a negative? We get negative. How about an 8? Positive. 9, negative. Even. Positive, odd, negative. Negatives raised to even powers are always going to be positive answers. Negative numbers raised to odd powers are always going to be negative answers. Negatives in front of numbers raised to exponents, that negative does not go with the number, are always negative. That's why we get two different answers here. That's why it's important to understand what's going on. So, big recap, exponents mean repeated multiplication. We have a base that's being multiplied by itself, however many times the exponent says. We can change repeated multiplication to exponents, or we can change exponents to repeated multiplication to figure out what they actually are. We can evaluate. What we don't do is we don't just multiply the base times the exponent. If we have negatives inside parentheses, being raised to an exponent, that negative goes with the number because of the reasons I explained to you. If not, that negative does not go with the number. We separate out the negative one. Order operations takes over. It says exponents first, then multiplication. Here, there's no way to separate that. That's a big deal. Lastly, we have something called, in our very first named rule, we got something called the zero exponent rule. Like, what the heck is a zero exponent? You can do that? Yeah. We have a zero exponent rule that says anytime you raise a number or a variable or anything to the 0 power, you get a very specific answer, and it's not 0. It's 1. What? That's weird. Why in the world do we get 1? No one knows. No, I'm just kidding. There's reasons for this, and I'll show you right now. I'm guessing you'll probably want to see that. So why in the world is a base to a 0 power 1? Well, it's because of division. Can you ever divide a non-zero number by anything and get 0? No. You can get 1, yes, but you can't get 0. I'm going to show you why that is. First, let's do some examples. I'm going to show you at the very end so I keep your full attention as a way to suspense this thing. Well, let's say that we have the following examples. And maybe one more. So let's use the zero exponent rule really quickly. How much is 5 to the 0? Anything to the 0 power is 1. How much is x squared y cubed over z to the 5th, or x to the 2nd power times y to the 3rd power? Remember, anytime variables are next to each other, they're multiplied. X to the 2nd power times y to the 3rd power over z to the 5th power is how we could say that. All raised to the 0 power. No matter what these are, anything raised to the 0 power is 1. Any non-zero thing raised to the 0 power is 1. How about negative 2 to the 0? Negative 2 to the 0. 1. How about this? Is this 1? Now this means that you got to understand some order operations. What do we have here with that number in front of our parentheses? We have that multiplication. So the way that order operations works out, very similar to why our 2's worked out so interestingly. This does mean 3 times 1/7 to the 0. That 0 is only applied to the thing in parentheses, not the 3. So we still have the 3. 1/7 to the 0, well that's 1. Anything to the 0 power is 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 1. But that 3 times 1 gives us 3. Now, why is that? I can give you a future proof that's like real rock solid, but it involves another rule that we don't have. So I'm going to do this through an exploration. So why in the world is it that a non-zero base to the 0 power is 1? Because a lot of people want to do 0. I did when I first saw it. Because my teacher told me so. Yeah, I'm telling you so too, but I want to show you why. So let's start with the 5. Let's do like 5 to the... That's might be too big. Let's do 5 to the 4th. What we do know is that anything divided by 1 gives us back that anything. So 5 to the 4th divided by 1 would still be 5 to the 4th. How about 5 to the 4th divided by 5? Well, oh man, what's the exponent of a number that doesn't have an exponent? It can't be 0, can it? Because anything to the 0 power is 1. So what do we have as an exponent for a number, for a constant number when we don't write it, or a variable, or anything? What exponent is it? Well, it's got to be 1. The interpretation is you have 5. What's it being multiplied by? How many 5s do you have being multiplied? 1. 5 squared would be 5 times 5. 5 to the 0 would be, how many 5s do I have? No 5s. I have 1. How? I'm getting to it. But that would be 5 to the 1st power. So any base that doesn't have an exponent listed has an exponent of 1. Now, what would we get? Well, we do know how to simplify fractions, don't we? If 5 to the 4th means 5 times 5 times 5 times 5, and 5 to the 1st means 5, we can simplify. Since everything's being multiplied, we can simplify, and what we get remaining is 5 to the 3rd. Looks pretty good. Does it look good to you? Hope it looks good to you. 5 to the 4th divided by 1, anything divided by 1 gives us back what we have. 5 to the 4th divided by 5 to the 1st gives us 5 to the 3rd. How about 5 to the 4th divided by 5 squared, or 5 to the 2nd? Well, our numerator's not changing. 5 times 5 times 5 times 5. Our denominator, well, we get 5 squared. What's going to happen? Oh, let's see. Our 5's, 2 pairs of 5s. 5 over 5 gives us 1. 5 divided by 5 gives us 1. We get 5 squared. Well, let's keep on going. How about 5 to the 4th over 5 to the 3rd? Well, okay, so that's, again, repeated multiplication here. We got 4 5s on the numerator. We got 3 5s on the denominator. And we can simplify three pairs of 5s. 5 divided by 5 is 1. 5 divided by 5 is 1. 5 divided by 5 is 1. 1 times 1 times 1 times 5 gives us 5. Okay, come on, put it together. 5 to the 1st. What is happening to our exponents? Well, when I divide by 1, 5 to the 4th, if I divide 5 to the 4th by 5 to the 1st, I get 3. We're basically subtracting 1. We're subtracting 2. We're subtracting 4 minus 3 is 1. So, the last one. 5 to the 4th divided by 5 to the 4th. Now listen, before you even jump to this conclusion, what's it going to be? What is something divided by itself? No matter what it is, as long as it's not 0, something divided by itself is 1. I know the answer to this question is 1. I know at 5 to the 4th over 5 to the 4th that you're going to get 1. But if you follow your pattern down, take away no 5s, you get 4 5s multiplied together still. Take away 1, you get 3. Take away 2, you get 2. Take away 3, you get 1. Take away all 4, you get 0. 5 to the 4th, 5 to the 3rd, 5 to the 2nd, 5 to the 1st, 5 to the 0. We get 5 to the 0, but I know for a fact that this creates 1 times 1 times 1 times 1 times 1. It's going to give us 1. That's a very kind of intuitive way to show that a number raised to the 0 power, as long as it's not 0, is going to equal 1. I hope that's interesting to you. That's kind of cool. That's why that is. That's one reason why that is. We can actually prove it by subtracting exponents. I prefaced that just a little bit, and we can really prove what's going on in that 4 minus 1 is 3, 4 minus 2 is 2, 4 minus 3 is 1, 4 minus 4 is 0, it's 5 to the 0. We also know that that equals 1. So that's the way that you would really go and prove that, and we can do it with any base. So I'm going to see you next time when we talk about some of the more specific rules. So we made it through 0 exponent rule. It's a big one. Get to know it, but really get to know what repeated multiplication is. It is an exponent, saying it properly, understanding what it really means. Yes, it's multiplication, but not those two numbers. After that, we're really focused on including negatives in parentheses, not including them with exponents if they're not in parentheses. And now we know about the 0 exponent rule. I will see you for talking about the product rule next time.